whatever we do, it's always aiming to a network of minimum cost. And if we only aim to a network of minimum construction cost, it is definitely a much more straightforward task. It'll be a short network. It'll be a network that avoids costly areas. So basically, it's just minimizing the construction cost part of the lifecycle cost. But when we also involve the reliability and other components of lifecycle cost, it'll be much more complex, because then we always need to balance in between that how much we invest and how much we save with those investments in terms of outage costs, for instance. So this is the other extreme, I would call it. So in this network we have, these will be the primary substations, these three corners here that are supplying the network. These will be the secondary substations that are consuming the electricity. We do have some parts of the network along a trunk line, like this one here. We do have an open switch here, normal open point, meaning that there is one feeder coming from this substation that is supplying this area in normal operation. We have another feeder that is supplying this part of the network in normal operation, and third one from this substation here. So in case of outages, we can of course use these open switches, so that, for example, if this line here gets faulted, we can open switches and isolate the fault, and then restore the supply for as many customers as possible from the reserve connection. So taking this into account in the optimization makes it more complex, but it really makes it more realistic also, because this is how real networks look like. Many of the optimization algorithms that I've seen in the literature, they only do something like this. You can get a network of minimum construction cost with it, but to be able to really plan a network that is fully taking into account all of the drivers that are really taken into account in network planning, you should come up with something like this. Our way of doing is involving this outage cost in the optimization, and with that we can find a balance in between optimally backing up a certain parts of the network and then leaving some of less critical customers and some costly locations outside of the backup. I quite often use a term operational environment, and that includes all of this. So regulator, environment, climate, electricity usage, different kind of uses, electricity uses in the future, like electrical vehicles, distributed energy resources as a production and so forth. This as a whole is the operational environment that really it's unique for each of the utilities. That is the basis for our modeling or parameterization for the optimizer. So once that's been done, it's actually pretty straightforward. But to be able to make a realistic and correct parametric model of the operational environment, that's not trivial. What I found during my doctoral studies is that I spent maybe, I don't know, 1/3 of time developing this actual algorithm. 1/3 of time I spent on figuring out what would be the parametric model for the operational environment. In the end, you always need to cut corners, you need to estimate, simplify, and you need to do it right, because, well, that's the kind of the tricky part, I think.